Have you ever been driving over a massive bridge and had that tiny thought in the back of your head, what's actually stopping this whole thing from just tumbling into the water? We see the giant towers and the thick steel cables, but what we don't see are the invisible forces, wind, traffic, even earthquakes, that are constantly trying to shake it all apart. Well, today, we're diving into the incredible and often invisible science that keeps these giants standing.
It sounds totally impossible, right? A 6,000-ton bridge? But it's not. It actually happened. Back in 1940, the Tacoma Narrows Bridge in Washington, a massive steel structure, was brought down by nothing more than a steady 40-mile-per-hour wind. This one event proves just how powerful these invisible forces can be. So, how in the world do we stop that from happening again? Well, to understand the solution, we first have to understand why bridges wobble in the first place.
All right, so our journey starts with a simple but super dangerous phenomenon, wobbling. It's really the first sign that a structure is struggling against forces it wasn't fully designed to handle.
And this wobble isn't some kind of design flaw, it's a fundamental property of physics. It's true for everything. Think about it. Just like a guitar string has that one specific note it wants to play when you pluck it, every single bridge has a frequency it wants to vibrate at when it gets plucked by something like the wind.
And this just goes to show the source of the shaking can be, well, pretty much anything. For the Tacoma Narrows, it was a steady wind. But for the brand new London Millennium Bridge back in 2000, it was just the synchronized footsteps of thousands of people walking across it on opening day. Totally different causes, but the exact same dangerous physics at play.
So, to stop all this shaking, engineers first had to absolutely master the science behind it. And it really all comes down to three key concepts.
First up, we've got natural frequency. The easiest way to think about this is to picture a kid on a swing set. If you give them one good push and then just let them go, they'll swing back and forth at a very specific natural rhythm. That rhythm is their natural frequency. And believe it or not, every bridge has one too.
Next is the real villain of our story, resonance. Let's go right back to that swing. What happens if you start pushing it at just the right moment every single time it comes back to you? It goes higher and higher, right? That's resonance. When an outside force, like wind or footsteps, pushes a bridge at its exact natural frequency, the vibrations can just grow and grow and grow, completely out of control, until the structure fails.
And finally, there's something called mode shapes. This just means that a bridge doesn't just vibrate in one simple way. It can twist, it can bounce up and down, or it can even snake from side to side. Each of these different wiggles is a different mode shape, and each one has its own natural frequency that engineers have to worry about.
So, okay, with all that science in our back pocket, how do engineers actually build a bridge that can conquer these forces? Let's look at a fantastic real-world example, Mumbai's Bandra-Worli Sea Link. I mean, just look at this thing. It is an absolute beast. It's a true reflection of modern infrastructure, a massive cable-stayed bridge designed to handle Mumbai's intense traffic and wild weather, all while sitting right out in the open sea.
And the scale of this project is, well, it's just mind-boggling. This was India's very first bridge ever built in open sea conditions. It's almost 5 kilometers long, needed 40,000 metric tons of steel, and was designed to handle 125,000 cars every single day. This isn't just a bridge, it's a massive, dynamic structure that has to deal with incredible forces.
So we've got the science, and we've got the challenge. Now let's get into the good stuff. How engineers put it all together to create a design that keeps those thousands of commuters safe day in and day out.
So here it is. This is the whole game, right here. The engineers have one crucial job. They must design the bridge so that its natural frequency, that rhythm it wants to vibrate at, is absolutely nowhere near the frequencies of the forces that are going to hit it.
And what's wild is they do all of this long before a single drop of concrete is poured. It all starts in the digital world. They create a perfect 3D model of every last nut and bolt. Then they use incredibly powerful software to simulate literally everything: wind, traffic, even earthquakes, to perform what's called a modal analysis and find those exact natural frequencies. Now, a huge piece of this design puzzle is the pylon. You can think of it as the bridge's backbone, right? It's the primary load-bearing structure. For the Sea Link, they use this amazing inverted Y shape, which gives it immense stiffness and stability, and that fundamentally changes the bridge's natural frequency.
And if you could peek inside the very top of that pylon, you'd find this incredibly complex anchorage box. This is mission control.
It's where all 264 of those massive steel cables are locked in, transferring the entire weight of the roadway up into the tower and then safely down to the foundations deep in the seabed.
The engineers ran thousands, and I mean thousands, of these virtual simulations, tweaking every little variable. And after all that incredible work, they finally landed on a single, critical number, the one number that proves this bridge will not fall down.
And here it is, 26.923 hertz. That is the calculated natural frequency of the longest span of the Bandra-Worli Sea Link. Now, why is this number so important? Well, it's because that number is way, way outside the range of frequencies that wind or traffic could ever possibly generate, which makes a resonance disaster like the one that destroyed the Tacoma Narrows Bridge practically impossible.
And you know, it's not just about the daily stuff like wind and traffic. Mumbai is in a seismically active zone, so the whole thing had to be designed to handle earthquakes too. And as the official analysis confirms, the design totally fulfills the highest standards for earthquake safety in India.
Okay, so let's zoom out and bring this all home. All of this mind-bending science and simulation, what it really comes down to is the invisible work of engineers. They're kind of like our silent guardians.
Just think about this for a second. What you're looking at here is a cross-section of just one of the 264 cables holding that bridge up. Each one is a bundle of super high-tensile steel wires, all precision-engineered to carry insane amounts of weight. It's this hidden complexity, multiplied thousands of times over, that keeps us all safe.
So the big takeaway here is that modern marvels like the Bandra-Worli Sea Link aren't just built to be strong. They're built to be smart. They're these incredibly complex dynamic systems, all finely tuned to resist and control vibration. They make sure that the dance between the structure and the forces of nature always ends with the structure still standing.
It really makes you think, doesn't it? From the skyscrapers we work in to the cars we drive, our world is just filled with this kind of silent, invisible engineering. So what other examples can you think of? What other things protect you every single day without you even knowing?